And now at this stage we can write down the two key equations that we've worked through, we've understood hopefully. The first one was to do with correlation, or the concept of correlation. We understood that x car was equal to c k or cl times tp, and we then related ck to our signal using this equation. And what this equation says to us is that we can take a signal, an analog signal, periodic analog signal, we can multiply it by a set of harmonics, sinusoidal harmonics, and integrate and scale, and we will end up with a set of weights. So this allows us to take an analog signal and break it down into components, and those components are CKs. So because we are breaking a signal down, we are analyzing it, this equation is known as the analysis equation for the Fourier series. The other equation was really an assertion at the beginning, which said that the analog signal, any analog periodic signal, can be represented by a set of harmonically related sinusoids which have been weighted appropriately. So this was the equation, and so what we're doing here is, of course, recreating or creating a signal by using a set of weights. So because of that, this is known as the synthesis equation. Okay, so we've not derived so much, but we've understood two key equations for the Fourier series. We've given two good reasons for using the complex exponential, because remember, it's easy to integrate and the exponents will add or subtract depending on whether we are multiplying or dividing. But why the need for cosines and sines, even and odd functions? Why not simply use a set of sines or cosines? So this is my third reason, by the way, for using the complex exponential. So let's illustrate that point or the justification using graphical means. So here I'm going to draw our signal. X of t now is just a sine wave. We're going to compare it against one of the harmonics, and that harmonic happens to have the same frequency. And if we remember, we're going to correlate, so what we're going to do is multiply these two signals together, which will give us something like this. And then, of course, we integrate, which means we take the area, and the result will be some value. It will be a positive value in this case, and that's great. It's given us a measure of the correlation, and you think, well, there you go. Why don't we just use sinusoids? Well, let's consider another case. So let me wipe out the signal. We'll draw it in a different color this time. Let's say the signal now is a cosine. So let me mark these important points. Makes it easy to draw. So the signal is now a cosine, like so. So what's going to happen now? when we multiply these two signals together? Well, let me get rid of this because it's going to confuse us. And let's mark out 4 quadrants which correspond to these points here. So for the first quadrant, we're going to get a positive answer, and then we're going to go through 0 here. So we're going to get a positive answer, go through 0, and then we're going to get a negative answer. We're going to go through, let's see, let's just delete that. We should go through a 0, I believe, here, here, and here. So now we will have a positive quadrant, 2 negative quadrants. So that's 1, 2, 3, that's 4. That's a positive quadrant. So let's see, we've started at a 1, and we want a complete period will occur here. So let's mark that. So that's a complete period at that point. So that's where we're going to stop. And what you'll notice is that, of course, when we add all these 4 quadrants up, then the answer this time will not be a positive answer, it'll simply be 0. So it looks like the correlation has resulted in an answer of 0, which can't be true because both of these signals have the same shape. They're simply shifted in phase. So this isn't the answer we would be looking for, and hence you can see that there's a need to use both odd and even functions. So we need an even and an odd function to basically make sure that we are not fooled by the phase shift. Okay. Of course, this relationship that we've just demonstrated is very important. Done a lot of work with quadrature signals in the world of communications with zero-IF and near zero-IF architectures, and there, of course, this relationship is crucial, and it allows us to, of course, send 2 data streams completely independently of each other using the same spectrum. That's going to conclude our video today on the Fourier series. Thank you for listening.